All right, so good afternoon, everyone. I think it's time we should get started on the afternoon session. So in this presentation, I'm going to be describing the progress we've made towards the next version of QMCPACK. I'm going to be giving sort of a broad brush overview of some of the updates, and then this talk will be followed by a presentation from Jaren Krogel describing how to drive this version of the code from Nexus and other details. And then Yelo will follow up with a presentation going into some of the performance aspects. So the outline of this talk is really very simple. I'm sort of going to go through the journalism W's, right? The who, what, why, where, when, and how around what we've sometimes referred to as the batch drivers or the performance portable code. So that's a little bit of a decoder wheel for you, or what will become version 4.0, which we're hoping to release early next year. And I want to start really with the summary, right? Whilst I've got everyone's attention, right? So what are the takeaways from this? Well, although a major impetus for this work was to ensure that we could take full advantage of GPU accelerated machines, this is a change in the code that affects everybody. So it affects CPU utilization as well. Hopefully only in a small way, as I'll be explaining, but it's important that using the code Productivity for Science, you try out a new version and provide some feedback. So that's really the main, my sort of main takeaway here is whilst other developers are here and we have the time at the workshop, please try out this version. I'm going to be explaining how to do that. And so to do that, you of course need to build and use the QMCPACK development version on GitHub, as I explained first thing this morning. That's really the preferred route since it has the most features in it. And in particular, you definitely need that for the updates to Nexus that have been done recently. So do clone the Git repository or do a pull to update and then rebuild from that. So this is not only a change in how the code sort of executes, sort of behind the scenes, but we have touched the input file. So in part of that is some sort of obligatory way so that we could tell the code to run sort of the batched version. But also there are some additional updates required because we're taking this opportunity to address some of the ambiguities and complications that there have been over the years. These are mostly simple updates, so let me touch on those. So first of all, to run this code, if you've developed, you put this driver version tag right up in the project section of the input XML, and that will switch to using batch drivers. There's other ways of getting to those as you'll see from the documentation, but this is the easiest and simplest way. And then you need to do possibly a few updates to the rest of the input file. And if you're doing a sort of standard, simple, vanilla VMC or DMC run, with just the energies, you have to do very, very little, right? And it's really only one change for diffusion Monte Carlo. If you have an older file that perhaps you're not even running in the current version of the code, then maybe updates due to how the basis sets are represented, and definitely the way observables are specified has been tightened up. This is actually all described in the manual and will help you with it, but I'm hopeful that if you're just doing a vanilla calculation, this is fairly straightforward. And what's the main required update for DMC? Well, this is sort of an example of one of our sort of thought processes for the updates. There's this input parameter called walkers, which has been very confusing, both the people inside the code and running it externally. And the question is, what is the normalization of this? Right? Is it the total Walker population, the population per MPI per thread? What's going on here, right? And this has tripped lots of people up, including myself over the years, editing late at night. This is a place we've taken the opportunity to add in, a new word, which is total walkers, which is the total number of the population, or you can specify walkers per task. So that's sort of the kind of update that we put in. Of course, one can do this by manually editing the input files, but I think this is yet again a very good case for having a workflow tool, because you'll be hearing in the next talk, if you tell the workflow tool to use the batch version, other people have done most of the work to do the updates for you, making things much simpler, more reliable. So what's the motivation for this? And I didn't know what Fernando had in his talk, but it actually set up this slide really quite well. And one of the main motivations actually is to keep QMC, the methodology, and QMCPACK running on modern computers and additional ones that we can see coming down the pipe. So particularly GPU accelerated machines, but of course we know computers will continue to change. GPU acceleration is becoming ever more common, of course. They're more power efficient than CPU. Sometimes they're not a lot faster, but they certainly are more efficient on the power side of things. And of course, we're all familiar with the advances in machine learning and AI, which is going to result in ever more machines with GPU accelerators on it and possibly other specialized hardware. And I think we all want to be able to take advantage of those to do our science and to run our quantum Monte Carlo. So, large CPU-only machines are becoming sadly rarer. They certainly have their place and advantages as well, but we need to make sure that the method survives, right, and stays on these machines. And just as an example, these are some examples from DOE in the US, but of course there's machines such as LUMI in Europe and lots of other investments already announced, machines coming online, such as Barcelona. So here's what we're looking at over here, right? So Perlmutter at NERSC on the West Coast is a machine with NVIDIA GPUs, AMD CPUs, and that's actually a very significant machine because anyone with some DOE funding can normally get a little slice of that machine. So there's no requirement to do a large calculation there. It's what's needed to do science. And even though there is a CPU-only partition, it's much smaller than the GPU partition. So being able to run on GPUs is very advantageous. Of course, Oak Ridge has got the first known exaflop machine in Frontier, and that's an all AMD system. And apparently behind us, and I think we're going to be seeing that tomorrow for the group photo, they're putting the finishing touches on Aurora, which should be a 2 exaflop machine, and that's an all Intel machine. So an additional complication here is that other players have entered the field, and there are multiple GPU machines around from different vendors, and we need to be able to write the code so that we can efficiently use all of them, right? So writing a custom version for all of these will be too hard. So this leads to the work on so-called performance portable version. What's the goals of this? I suppose this is a little bit hidden from you if you're just running the code, but if you're developing, this is certainly very important. And the goal here is to get as much as possible a common code base for all of these platforms. So we don't need to have 2 different versions, 3 different versions, 4 different versions of the software. And this is something that hasn't been achieved before in these kind of ab initio QMC codes. But we don't just want performance, right? The code's got to be productive for science. And one of the key factors going in is that all features will always be available. So they will always run, fallback to running on CPUs. It won't be that the code will just stop and say, we don't know how to do that on this particular GPU system. So the results might not be as fast as could be achieved potentially, with more optimization development work, but we should always be able to run and get our science done, right? That's what we're here for. Of course, we want good performance on GPUs, but retain all the excellent CPU performance. And then some other updates we're sort of making as we're going through this to begin to have more checking of the inputs. It's something we've certainly heard about. Some more error checking. Hopefully people have seen that. Doing that better can be done historically. And this is something that's going to help us build more automation into the code over the long term. I personally would like to have lots of defaults so that doing a run with reasonable performance is really straightforward and we don't have lots of settings to scan through. Of course, if you want to do that, that option will be there, but I would like the automation. This is what we need to do, that sort of high throughput work and reduce the burdens on the humans that Fernando was talking about with self-healing, for example. And just a flavor of some other updates, we want to move towards more compile time options. I don't know if this will make 4.0, I hope it does, but only having one build of the code, I think, would be a nice simplification as well. So those are the goals. So what are the features that we expect to have in this sort of 4.0 version? And looking over the published papers, I think it's fair to say, everything needs to do the majority of recent publications, so about 19 out of 20. And I can say that because about 19 out of 20 publications are either on molecular systems or materials with periodic splines, VMC and DMC, really the core functionality. And that's going to be there, right, from there on. It's there right now. So, so I can say that because the core features, are going to be available, maybe highly accelerated or partially accelerated, but, you'll be able to run. So what will be in there, and it's actually in there running right now, VMC, DMC, wave function optimization. That's relatively mature overall. Spline basis sets, they're very performant for materials. And then there are some new features coming with this version of the code. So there's an early accelerated version of Gaussians or LCAO basis sets, and also multi-determinants. So there's the beginnings of an accelerated molecular code in here as well. So there's functionality there, and we're going to see how it performs in the real world on all these different systems and then set about optimizing. But obviously we want to support that. There will, however, be a more limited selection of observables. So we're going to have the core ones, such as electron density, and then there's going to be about one example of each computational flavor of observable, such as the density matrix, for example. That's a computationally expensive one, and that's been worked out. And then also some of the features that are going to be discussed tomorrow, or the features that will be discussed tomorrow, are also runnable from this. And of course, we're committed to supporting and improving this long term. So that's 95%. So what won't be in this sort of initial version, and of course, this is open source, so we're very happy to help with contributions, because it's not that we're stuck in any way. That's not why certain features aren't going to make it for the first version. It's just there's only so many people available with a certain amount of time and a certain amount of funding. So we've got to sort of draw the line somewhere. I'm sure everyone can think of other pieces of software that have done this sort of thing. But we do want to make sure that, what's not in this first version is sort of more of a minor feature, a little bit more obscure. So for example, the code does know how to do all particle moves, which in the Monte Carlo, which is something that you tend not to do in production because it's less efficient, but it can be quite useful when you're developing a new method, for example, but that won't be there. Reptation won't be there. Backflow optimization isn't there. This is a big simplification because it basically halves the amount of code that was needed due to the way it was implemented historically. I touched on the observables, and again, some of the less, more obscure features won't be there. So what's then the plan? Well, these get deferred to, the point one, I think it should be fairly obvious. And then we're really going to listen to see what the requests are, what would unlock the most scientific impact, for example. So if you find something isn't implemented, that would be really helpful, is really critical for you, let us know, vote, essentially. We want to address those. And obviously over time, it will become ever more complete. So what is the status of today's development version? What I would say is that production science has been done with this version. I think that's important to note. But things like the energies seem to be good, and the test sets that we have are passing. So we're not at quite the same level of testing as we have for the older drivers and the older code, but we're quite close. What do we have to do before this new version? While making these drivers the default, and just to be clear here, we're going to remove the old paths, right? If you need to use the old paths, use the previous release of the code, that's still there. And we're doing that because it's a huge simplification internally, right? This will get us to the one implementation of most things, which is a big productivity improvement. And it will also allow a lot of cleanup and refactoring to happen. So again, please try out this new version. Of course, we want to expand the test coverage. There's going to be lots of updating to the documentation needed. And then most importantly, there's no substitution for using something out in the real world, to do some actual science and production calculations when you really want the answer. So that's what we need to do. And of course, importantly, we're going to listen to what feedback people provide. So if there's some big problems found, we're of course not going to be releasing this. It will delay and fix the issues. But I think right now they tend to be, if they are problems in there, they're going to be more corner cases, right? We know the energies seem to be good, but maybe there's some input passing which isn't right, or something like that. And hopefully if we learn about that, it'll be a quick fix. So do let us know. And as I said, we hope to get this out early, in quotes, next year. So what does it mean to do a CPU run with this code? You know, if we want to run this on our laptops, what do we need to do? So of course, this is going to be touched on in the subsequent talks, but basically, if you have vanilla inputs, you need to put that driver version parameter in there. If you're doing DMC, you'll have to, you know, change that Walker's tag, otherwise the code will complain to you. That's sort of a new thing. And then I would suggest you just run as before, right? If you've used the same number of MPI tasks, if you've investigated threading, use that, leave it there, and that should work. And it will work, and it'll get a basically identical performance to the old version of the code. That's how it's meant to be. Now, I am making a simplification here. I said this was a broad brush talk, so to provide not too much information in this talk, I'm not going to go into a new parallelization level we have in the code called crowds, which potentially might get a little bit of extra CPU performance. But if you're looking in the manual and you see references to that, I would say start with one thread. And if you really want to tune for the last 10%, 20%, there are some extra options there. This is more important for GPU. So you know, this code has also been referred to as the batched code. You know, what is this batching and why is it important? And of course, I should say the CPU code is, of course, going through the batched code, except the batch size is 1. That's the difference. And the difference basically comes from the characteristics of the GPUs on these systems, because when one zooms out, right, all of these GPUs from different manufacturers have many common features, right? And one of them is just the sheer scale that they have. So the number of computational elements that you need to keep busy to get high performance, right? Otherwise, it's like using only 4 cores on a 16-core machine, right? You can't get more than 25% efficiency if you do that. And so just an example, you know, the other week, AMD announced their sort of new GPU, and this is going in a machine at Livermore, and it has nearly 20,000 stream processors on it, so simplified compute elements. So clearly, you need 20,000 things to work on to satisfy this whole chip here, and it's going to be actually many more. So, you know, I've noticed here at least 10 to the 4 similar operations in flight. This is being very conservative. It might be 1 million, right? So how do we get this work? The issue we have to face is that if we only have 100 electrons, even if we're doing n² work, for example, that's never going to be enough to satisfy these GPUs and hide some of the other things that we need to run efficiently. So the trick, and I should say this was worked out basically a decade ago by Kenneth Esler, and there's the publication on that, is to write the code to work in batches or groups of walkers simultaneously. So the updates that each walkers are doing can still be different, but the code is going to work on a whole block of 100 or 1,000 walkers simultaneously. And if you do 1,000 times a few hundred electrons, now this is about the right size to fill these GPUs. So that's what's going on. It's not a fundamental change to the Monte Carlo at all. It's just a way to the way the code is written and how it executes on the silicon. Of course, doing this to support all functionality, which is what we've done now, or we're sort of working on, is a huge update. So the drivers of the quantum Monte Carlo are different. The APIs for how wave functions are evaluated are different. And it runs all the way through to how observables are done. So this is quite a big update that's happening behind the scenes. And if you've been tracking the changelog and releases, we've been chipping away at this over the last several years. And just a note here, so people are thinking about sort of the right numbers. If you do want to run on GPUs, we know from these numbers here that, well, if you don't have many electrons, you're going to need thousands of walkers in the batch, and maybe not millions, but thousands, right? So whereas if you have a larger number of electrons, you'll then need a smaller number of walkers. So that's the balancing that's happening here. And of course, small electron count problems are going to be quite hard for us to accelerate because there's less compute work on them, and CPUs are still very good for those. So what do GPU runs look like? Well, and how do you run them? Well, you do the same change to the input file that you did for a CPU run. You say, give me the batch driver at the minute. Of course, in future, that will be the default, but with the development version, that's what you need to put in. And then the one change you need to do is to specify a number of walkers per rank, or total walkers, as I've been discussing, to be a reasonably large number, as I was just describing. So if you have 200 electrons, it might be 1,000. If you have 2,000 electrons, it might be 100. And where does this number come from? Well, that comes from what the performance looks like on GPUs. And remember, you don't have to do this for CPUs. This is a GPU specific thing. So what I'm showing here is a performance result from the current code for 32 atoms bulk of nickel oxide. And on the bottom here, the x-axis is the number of walkers in the batch. And the y-axis is throughput normalized per walker. So higher is better. And what we see here, if we look at the green, this is the current code, right? We see a steady increase, right? Or I should say an increase in performance. So it's nearly saturating at 2,000 in this case. If you had 1,000, maybe you're 80% of the way there, but obviously if you put 100 or 10, you're missing out on a large amount of performance. I should say you don't necessarily always get this curve. There can be bumps in it and so on, depending on the system and what's being run. But you always have the case that more walkers will lead up to some sort of plateau, and that's where you should take. If you go too far, maybe it comes down. It depends on the system, and importantly, what fits on the GPU. So this is the part that's not automated currently, that we'd really like to automate. One has to scan for the best throughput. Normally, that's the most number of walkers that you can fit on a GPU before you run out of memory. So of course, you run until you run out of memory, and then you back off. So that's one additional step, unfortunately. So it helps to have some automation to do this if you're running on GPU systems. And again, CPU-wise, you don't need to worry about this. And again, for GPUs, my take, this is what I do. Start with one GPU and one thread per, one MPI per GPU and one thread per MPI. And start there, start doing some production science, and then you can look at some other options to perhaps get 20, 30% extra performance. But this should be enough to get you up and running science. So, what's the state of the GPU version? How do you build this? You've got access to a GPU machine. Well, there's already examples of this in the manual. And as I mentioned this morning, the config directory has got built scripts for some common supercomputers, and also some new supercomputers. So Frontier is in there, for example. Now, what's the status of running? And I would think most people are focused on NVIDIA systems currently. And the good news is that the code works really well and is performant with running on NVIDIA with sort of the latest software. So recent LLVM compiler and the latest releases of CUDA, which is NVIDIA's GPU software. So that works really well. And so the runs are good on the Perlmutter machine that I was just, the Polaris or Perlmutter machine that I described earlier. Now, what is the situation on the other vendors? Well, to be really honest here, the vendors still have some work to do. There are still a few issues on AMD. They've been very close to us being able to say the same thing as NVIDIA has been able to say, but they're not quite there. They just did announce a big update, and when we try that, this is ROCm 6, fingers crossed, they have fixed all the problems that we need fixed. It's very close, and I don't think we need to change QMCPACK at all, so the ball is in their court. That said, there is a Frontier recipe in the config directory. Intel, as you would expect, also need to do some updates, but they're getting ready to release Aurora to the masses behind us, so they're very focused. And what I would say is if you're interested in running on machines with these other vendors, such as Lumi, which is an AMD machine, talk with us for the latest recipes and whatever the current caveats are, because this is changing and improving all the time. And then what of course we're going to do is when we've heard from people running on these machines, we will do some optimization based on the feedback. So if something seems slow, or you see some odd behavior, let us know. The key thing is to have science underway, right? That's what we're here for. And maybe we get a factor of 2 or 50% in the future, but the goal is, have good energies, densities, results we're confident in and can publish on safely. So some notes on documentation. The links are here in the PDF that you can click on. I'll show you where to click in a moment. So this is described in the manual, and it's described in a bit more detail than I've done here. So there is a section on performance portable version in the manual that goes through a few more details and has got links. And also all the individual drivers as a way to run like VMC batched independently, for example. That's all described. And there's also tables of the parameters that are accepted by the new drivers, which are similar but not exactly the same to the old ones. As an extra note here, more details of the design are in this paper published by Yale conference proceedings, and the link is here. So if you put that in Google Scholar, you should find it. If I just show you now where to go in the documentation, if you bring up the QMCPACK.read the doc site, you can see here in about the 3rd chapter, there's a note here on the performance portable implementation and some of the changes that are needed. So just to sort of begin summarizing and wrapping this up. So this change really affects everybody, and we are keen to have everyone try it. We're quite excited about this new version. There's been a lot of effort going behind it by a lot of people, but nothing is going to be running it in the real world and getting everyone's feedback. So in the time we have in the late afternoons at this workshop, please try this out if you've got the time. Certainly, as soon as possible, please try this out and get us feedback, ask whatever questions you have. Some input updates will of course be needed, but we hope this is simple for everyone. It's also a very good example to use a Nexus or a workflow tool. So I'll just open it up for any questions at this point. And I know that was a lot of information, but I hope that was a sort of reasonable, balanced, broad brush view of what's going on with this new version. All right, I see there is one question online, and that is there a way to anticipate a ballpark value of walkers per rank based on the GPU architecture itself? I think one could build a performance model to do this, but the easiest thing, it is much easier just to have a script or some automation workflow to scan for the number of walkers, because when one is doing a real run, there's often additional complications. So for example, you might add an observable to measure the energy density, to the electron density. And that, of course, affects the performance overall. So trying this thing out in the real world on the computer you have and not in a model is the most productive way. If someone wants to do some research looking into the details, everyone's very welcome to do that. And there was a question at the back, but you don't have a microphone.
Thanks. So for the batched code using a CPU, more conventional architecture, do you have to do the same kind of walker per rank scan? Or is it kind of different in that sense?
Good question, Josh. So no, you do not need to do a walker per rank scan. It is just the same as CPU runs that have been run for a decade. So keep the same total population of the walkers that you've done historically, and everything will work just the same. This is purely to run efficiently on GPU and accelerated architectures. Right. What does tend to happen is that when you run on, so nothing changes on CPUs, but when you run on GPUs, you tend to have a much larger walker population. That's something we're going to have to learn to live with.